So today we'll do we have done two sessions on solid mechanics, which is otherwise called as strength of material or mechanics of material. So it's a very important subject. You can say the foundation of mostly the structural designer, be it a mechanical engineer or be it a civil engineer, any structural designer, even an aerospace engineer, any structural design, this is the foundation. Okay, so um, like whether a, a mechanical engineer is designing an aircraft or designing a car or automotive or designing any mechanical structure, a machine tool, uh, anything you are designing, you will see what kind of load is there on the structure. Okay, whether the structure is able to withstand that kind of load. So for that you need to know what is the strength of the material. That's why we call it as strength of the material. Okay, this mechanics of solid is otherwise called strength of the material. Okay, so yeah. So that's why we had, when we studied about steel, we were talking about two strength. One you were telling us the yield strength.
and ultimate
Another we were
strength.
telling us the ultimate strength. So for certain design we will be referring to yield strength. For certain design we will be referring to ultimate strength. So ultimate strength is the maximum strength that a structure can carry. Okay. Yield strength is the strength beyond which the material is going to yield. So there will be some permanent state, permanent deformation even if you have to remove the load. So in many structural applications that is not required. I mean that is not acceptable at all. Okay. So after you remove the load, it should come back to its original position. It should be elastic in nature. It should operate within the elastic limit. It should not yield. And in some structure, it is acceptable. Okay. So in those cases, we use ultimate tensile strength. But normally we operate it within yield. Okay. There are some certain things where we get into plasticity also. Means more loads are applied and we get into plasticity also. That is there for some structure, like say aircraft engine operates at very high temperature. Like it may operate at 1200, 1300 degrees centigrade. So any turbine has a wheel and it has a blade.
Yeah.
Okay. So when the wheel rotates at 10,000 rpm, 11,000 rpm, huge centrifugal force will be acting on that wheel. So the stress will be very high. So under very high stress, as you know, in the stress strain diagram we have seen, as you keep on increasing the load, the strain increases. So when you apply more load, the deformation increases. Okay. So if you are operating under very high heavy loading condition, so there are chances that it will exceed the yield point and it may go into plasticity. So then these are functional requirement. You cannot avoid it. So we operate at high temperature because if you operate at high temperature, your efficiency will increase. Okay. So like if you operate at high temperature, your efficiency will increase. Okay. So you might have studied about 1 minus T2 by T1, that Carnot engine efficiency. Okay. So the more bigger is the T1, the source temperature. If it is high, that term will become low and your efficiency will increase. So more is the source temperature or operating temperature, better is the efficiency. So what is efficiency? Efficiency is nothing but how much thermal energy or chemical energy you are able to convert to work. So you have studied that efficiency is equal to work done by heat input. Okay. So work done we have studied is equal to Q1 minus Q2. Okay, divided by Q1. So in Carnot we have done that 1 by Q2 minus Q1. Then we have proved that 1 minus T2 by T1. This is what we have proved for Carnot efficiency. So this is the sink temperature. This is the source temperature. Right? So I had drawn, right, this is my source and this is my sink and there this is the engine here. So I am supplying some heat Q1, I am doing some work W and I am again rejecting some heat Q2 into the sink. Okay. So the source is at a temperature T1, the sink is at a temperature T2. Okay. So if this is the case, I know if T1 is high, T2 minus T1 will be low. If T2 minus T1 will be low, if T1 is high. Then that means 1 minus T2 minus T1 will be high, right? Because it is a minus sign. High. So my efficiency will increase. So that's why we have to operate at high temperature for functional requirement. So when you are operating at a very high temperature, like say 1200 degrees, when aluminum will melt at that temperature. So when you operate at a very high, so the turbine actually it looks like this. So you have a wheel and you have so many blades here, blades. Okay. So you have a wheel and you have a blade. So this turbine, what does it do? It gives work. Turbine is something which gives work. What happens actually there? High pressure, high temperature fluid will see the go through these turbine blades, and that high pressure, high temperature will drop in that. That pressure energy will get converted into velocity energy or whatever. So it will rotate the turbine. So you might have studied in second law of Newton. Okay, rate of change of momentum is equal to force. So suppose you have if you take the cross section of the blade, so it's let us say in a Pelton wheel or in an impulse turbine, the blade looks like this. So it will enter at a velocity v1 and it will go out at a velocity v2. That means even if the magnitude does not change, the direction is changing. So it is like, let us say an extreme case. It is going like this, it is coming like this, it is going like this. So in this case, what is happening? Because there is a 180 degree change in direction. So because there is a direction change, that's why there will be force.
Understood.
So you know second law of Newton, rate of change of momentum is equal to force. What does that mean? Like mv2, let us say this is v1, this is v2. mv2 minus mv1 divided by time. Okay. This is the rate of change of momentum is equal to force. Okay. So you know m dot, so m by t into v2 minus v1 is equal to force. Okay. So m dot t is otherwise called as mass flow rate. Mass flow rate. You are understanding, na?
Yes.
Any confusion here?
No.
Second law of Newton I am telling you.
I know.
There are three laws of Newton. First law, second law, third law. First law is the law of inertia. Okay. If a body is moving at constant velocity or if the body is at the state of rest without application of external force, the velocity is not going to change or the state of rest is not going to change. First law. Second law, rate of change of momentum is equal to force. The concept of impulse and other things comes there. Then the third law, each action has equal and opposite reaction. So you are firing a bullet, okay? Then that bullet, the gun is going to hit your chest if you are not strong enough. That means the bullet is going in the forward direction, whereas it is pushing the gun in the backward direction. So if you are not strong enough, the gun is going to hit you. Similarly, you might have seen the rockets. Okay, rockets. So from the back side, you can see the gas, exhaust gas is going out. So it is propelling the rocket in the forward direction. So you might have seen this. You will study about the escape velocity, the many other things like what is escape velocity. That is maybe 11.2 km/h. We derived that. So at escape velocity, the rocket will escape from the atmosphere of Earth. It will get into some other orbit. Okay. So you will have multi-stage. Rocket, like one after another. The one stage will go, then another stage will go. Once it goes, the velocity keeps on increasing. So after firing of all the stages, there will be a chance that it will reach 11.2 kilometer per hour, and that it will escape from the atmosphere and it will get into the orbit of some other satellite. It will be orbiting around moon, or it will be orbiting around some other satellite and all that. And there are something called escape velocity, and there is called something called the orbital velocity. So after reaching a particular velocity, it will start orbiting around the Earth itself. Okay. So those are all the principle of operations of a rocket is third law of Newton. Okay. Similarly, the aircraft engine. Okay. So because I come from aircraft engine specialization, I will say, like, when in an engine the exhaust gas is going out, it will propel the aircraft forward. That is the principle of jet engine. So you take some air, you put some fuel, you create some gas, high temperature, high pressure gas. That gas passes through turbine, some work you derive. Still after extracting the work in the turbine, still some high pressure, high temperature gas will still be there. So that pressure temperature it will be adjusted expanding in a nozzle. So it will give rise to a high pressure, high velocity gas. So the velocity at which the gas is entering is less than the velocity at which the gas is going out. That's why there is a change in momentum, and that rate of change of momentum is equal to force. Okay, so we are deviating from the topic what we have planned for today. So I am just telling mass by T into V2 minus V1 is equal to force. Okay, so what does this, you might have studied about impulse. Okay, impulse.
Or mass into V2 minus V1 by T, mass into acceleration.
Sorry, V2 minus V1. That is also fine. Okay, so that is another way, this is another way.
This is for impulse.
Mass into V2 minus V1 by T is nothing but your acceleration. So ma is equal to force. Okay.
Yeah.
So I am telling impulse thing, what happens now when a cricketer catches a ball. So that if the time taken to catch the ball, he is pulling down his hand, because the time period he want to increase. So if he is increasing this time period, he will get less hot. He will not
the
hot.
The force that he experiences will be less.
So the force will be less if the T is more. Okay, that is. Similarly, if you are jumping and you are jumping onto some heap of sand, what will happen? Because the time you are jumping onto a concrete floor and you are jumping onto a heap of sand. Suppose you are jumping from second floor, third floor. Luckily, if sand is there, nothing will happen to you. Because the time period, from the time he touches till he comes to rest, he touches the sand till he comes to rest, that time period is very high there. That's why he is less hot. He is not, nothing is happening to him. Okay, but if you are jumping on the concrete, your legs or your body will get fractured. Okay, so that is okay. So we are deviating too much from the topic. Okay, I was from temperature itself. I have come this far. Okay, can you take a picture and we will get into the other one. So we'll cover what is Poisson's ratio. We'll cover what is what is strain energy. So those things we need to cover today. Quickly we will cover those things today because there can be many numericals on it. So the intention behind understanding all this finally boils down to solving some numericals. So that is how the process is nowadays MCQ pattern of study or pattern of examination. So you don't mostly you may not do derivation, but you should know the formula and all. Okay. So Poisson's ratio. Okay, let us study what is Poisson's ratio. Poisson's ratio. Okay, what happens? Like, let me say I have a I have a rod like this, and it is being supported at the top like this. Okay. So what happens if I put some force on this? If I put some force on this, it will try to elongate. Okay. When it is elongating, in this direction it will get contracted also. Okay.
Yes. Like making.
Yeah. So when it is getting elongated, it will get contracted in this direction. In this direction, what will happen? I am just putting a exaggerated picture. It may not be this much of exaggeration. So it will be just putting an exaggerated picture. So it will get elongated, right? Clear?
Yes.
It will get elongated. It has got elongated, right?
Yeah.
So what you can see here is, let us say this elongation is delta L. Okay. Then the original length is, let us say, L. And let us say the original diameter is capital D. Okay. And then this plus this.
Del D.
This is like say del D, del D. If you add both the things, it will be del D.
Okay. Yeah.
So okay, so del D. Okay. So what is happening here? There is a longitudinal strain. Longitudinal strain.
Yeah.
Which is nothing but your delta L by L. Which is E or whatever.
Yeah.
Okay, then you have a lateral strain. Lateral strain. Which is
Del D by
del D by D. Del D by D. It is always negative because it is getting compressed, na?
Decrease.
It is decreasing, but length is increasing. That's why it is positive. Then what is Poisson's ratio? Poisson's ratio is equal to lateral strain by longitudinal strain. Longitudinal strain. So that Poisson's ratio is otherwise referred to as mu. Okay. So this Poisson's ratio is otherwise referred to as mu. Okay. So I can write it as like this: mu is equal to delta D by D divided by delta L by L. So and this is minus. Okay.
Yeah.
So this is called your Poisson's ratio. Okay. So the typical value for steel, the Poisson's ratio is in between 0.28 to 0.3, and for aluminum it is about 0.33. So typical value, just remember for steel. So nu of steel is in between 0.28 to 0.3. So you always remember Poisson's ratio is a ratio. That's why it is called ratio.
Yeah.
It is always less than 1 and it is in the range of 0.28 to 0.3 for steel. And for aluminium, why are you referring steel and aluminium? Because for most of the structural material we are using steel and aluminium. For aircraft we use aluminium because we want the aircraft to be lighter.
Yeah.
Otherwise, for ground-based application, mostly you are using steel, which is the highest strength.
Because it's alloy.
It's an alloy of iron and carbon, and there are many other alloying elements like say chromium or nickel or many other alloying elements are put to improve the strength of the original material. So if you keep on changing the percentage of aluminum alloy, you will get different strength. Okay, so that's steel is a alloy of iron and carbon along with some other alloying element.
Yeah.
So Poisson's ratio of aluminum is 0.35. Okay, that is one. Sorry, 0.33. 0.35. Okay. Okay. So why do we need to know Poisson's ratio? We have not derived it in mechanical engineering or civil engineering. We derived it. G is the rigidity modulus is equal to E by 2 into 1 plus mu. That we can derive. Okay. So
for any material.
For any material. This is the relationship. So it will become like E divided by 2 into 1 plus 0.3. So it becomes is equal to E into 2.6. So that means E is 2.6 times higher than G. Just remember, this is not in your scope actually. So Poisson's ratio of aluminum is 0.33. This is just a value to be remembered, which will be may come in your exam. Okay. Okay. So we have completed Poisson's ratio. Okay. So Poisson's ratio is nothing but lateral strain divided by longitudinal strain. So you take a picture of this. So we have finished Poisson's ratio. Now we do elastic potential energy in a stretched wire. Okay. We'll do elastic potential energy in a stretched wire. How much when you are stretching a wire, there will be some energy stored in that wire. How much is that energy? That will do. How much is that energy? That will do.
Black pen red light.
Okay, fine. So we'll do elastic potential energy. That is also one important concept. So whatever formula you are writing, you write in your whiteboard, drawing sheet. Every chapter wise, every chapter will have 5, 6 formulas. Also in your NCERT book, you can see at the end of the chapter they are summarizing the things. That also you refer. Okay. See, before giving the exercise, they are also beautifully summarizing whatever they have taught in the chapter. So rather than going into the detailed derivation, now is the time to just see what they are writing at the end of the chapter. So NCERT is doing that actually. They are summarizing at the end of the chapter what they have taught. Right? You might have seen that, right?
Yeah.
Beautifully they are doing. Inside the chapter there are some solved numericals. If you refer that, so 2-3 numericals they are giving, and they are in the exercise they are putting 15-20 numericals. So they are giving the hints actually. They are doing their job. Okay. So elastic potential energy in a stretched wire. Okay. Elastic potential energy in a stretched wire. Okay. So when a wire is put under a tensile stress, work is done against the interatomic forces. Okay. So let me say again I am drawing. So let me say that this is a wire. Okay. So I am putting some force F here. Okay. So this is a wire, and let me put some load like this. Okay. Some load. Okay. So this load is causing some force, right? This load, let us say W, which will cause some force, which is equal to some force. Weight is nothing but force.
Yeah.
You are putting some force. So when you are doing some work, it is done against the interatomic force. So every wire or every structure will have some atoms. Okay. So these atoms in solids, they are very close to each other. The interatomic force is very high in solid. The interatomic force is little less in liquid. So the liquid will take the shape of any container. Okay. Whereas solid does not do that. It will retain its own shape because its interatomic force is high. Whereas gas, it does not take the shape of the container also because the interatomic force is very less as compared to solid and liquid. Okay, so when you are stretching it, you are doing it against interatomic force. So you are, when let us say this is the distance. So when you are stretching it, you are trying to move this atom little far. Okay, so that is happening. So when you are doing some work against interatomic force, there is some work done. Okay, so this work done is stored in the structure in the form of potential energy. Okay, so let us say there is a force F acting here. Okay, now you have moved this atom by some distance d. So you have done some work F into d. Okay, so this work is getting stored as potential energy in the system. Okay. Okay. When a wire of original length L and area of cross section A is subjected to a deforming force F. So let us say this area of cross section of this wire is A. Okay. And length is L. It is subjected to a force F. When this happens, A subjected to a deforming force F along the length of the wire. You are applying the force along the length of the wire. Okay. Along the length. Then the length of wire, be elongated by small l. Okay, let us say capital L is the original length, small l is the elongation. Okay. In that case, how do we write it? That force. So we know like stress by strain is equal to Young's modulus. Let us write it as Y. Okay. So stress we know as F by A, right? Strain we know in this case as small l by capital L. Okay. So my F by A divided by small l by capital L is equal to
Young's
Y.
modulus.
Y. Okay. So this. So F by A is equal to Y into L by L. Then F is equal to Y into A into L by L. Okay. So this is the force. Okay. So when Y is the Young's modulus. Okay. Now further elongation of small length dl, work done dw, and okay. So what is happening? So this is the equation for force. So if I elongate my, let us say it is in elongated position. Now I further elongate it. Okay. Let us say this is capital L and this much is small l. And then let me say I further elongate it by some dl.
Okay.
This is further elongating by dl. Okay. So if I further elongate it, what will happen? Work done is equal to F into dl.
Yeah.
This is the infinitesimal work.
Yeah.
Because that side is d, this side is d.
dw.
dw. Okay. So what will happen? So this is the thing. Okay. Then suppose it elongates from small l1 to small l2 or whatever. Initially it is like dl. So elongation further elongating it from L1, small L1 to small L2. If that is the case, like, or you can say that And the initially the elongation is 0, finally the elongation is small l.
L.
So that total work done is equal to integration of dw, which is like y into a into y into a, okay, y into a, and you know here like f is equal to y into a, uh, dl dl, okay, dl into l, okay, l dl, right? You are just substituting it.
Yeah.
Y a l dl, because I am putting dw is fdl, okay.
Yeah, yeah.
So f you are putting y into a into l, okay, then divided by capital L, right?
Okay. Yeah, yeah.
This you have just substituted, okay.
Value of f.
So your W becomes finally, it will like say y, a and capital L will go outside.
Constant.
Okay. Then integration of L dl. Okay. So it becomes y into L capital L. Then you know x to the power n dx integration is equal to x to the power n plus 1 by n plus 1. Right?
Yeah.
That you know.
Yes,
Right?
yes.
That is the integration. So here it will become L to the power
L
1
square.
actually, so it will become L to the power 2 by 2.
2.
So it becomes work done, total work done is equal to, so this W is nothing but integration of dW, okay, from 0 to L, like the dW from 0 to L. So it is from 0 to L.
Okay. Limits.
So after you integrate, so the formula will become half y L small l by capital
No. L square.
uh, L square by L. Okay. So what I can do here, I can write it as y L square. Okay. So integration W is equal to what? Okay, let me write it like this. Y a L square by W. So y a by 2, y a by 2 L square by L. This is the formula. Okay. So what does it become? Half y. So this is y. So it becomes half y. Then so you can write it as L square by L square into capital L. Because below L, on the below you multiply L, on the top you multiply by L. So it becomes half y into small l by capital L whole square, okay, into any area you have left us.
A
So,
into L.
A into capital L. So your total work done is equal to half uh, half half y into small l by capital small l by capital L whole square into capital L into A. Right? Right? No?
Yes.
For this line is something. Okay, see, this is how I have derived. Okay.
Yeah.
So work done is integration of dw from 0 to L, integration of dw from 0 to L, and then dw so dw is nothing but your FDL or whatever. Then F I have got as YAL. Okay. So YAL has come here and small l go there. Then YAL square by capital L. Then on the top capital L, on the bottom small l. So you got half Y L square by L square and L into A. Okay. So finally what it is? Finally what it is finally half into Young's modulus into AL into L by L whole square. Okay.
Yeah.
So this is what you have got. Okay. So this L by L is nothing but your strain.
Yeah. Change.
Are you sleeping?
No.
So L by L is nothing but your strain. Okay. Half into Young's modulus Y into strain square into volume. AL is the volume of the wire. Okay. So this strain Young's modulus can otherwise be called as stress by strain. Stress by strain. Okay. Into E square into the volume of the wire. Okay. Into the volume of the wire. So this you have derived arc is equal to this much. You have derived arc is equal to this much. Work done for elongating a wire by a length small l. Work done for elongating a wire of length capital L by small l is equal to half sigma into sigma by E into E square into volume. Okay. So if you see here, look here. It is in denominator you have epsilon, in numerator you have epsilon. So your work done will finally become half into sigma into epsilon.
Into volume.
Into volume. So this work done will be stored as potential energy. So if you say what is the energy stored for unit volume, that becomes half energy stored for energy per unit volume is equal to half sigma into E, stress into strain. This is the energy per unit volume. Energy stored per unit volume. Energy stored per unit volume when you extend a rod or a wire of length capital L by small l is equal to half stress into strain. So stress you know F by A, strain you know small l by capital L. So this is the formula. So you can take a picture of it. So we have derived, okay. This energy is otherwise called as small u, something that you derived. So you have derived the energy stored per unit volume in a wire of length capital L elongated by small l. Okay. So it is 40 minutes. Will we do more or we'll have another session? Will we do more or we will do another session?
40 minutes each.
Okay, so I'll solve few numerical before getting into other concept. Okay. Quickly I'll do some numerical. Okay. Quickly I'll do some numerical on modulus of rigidity and strain energy. We'll do some numerical quickly. So in another 10 minutes. Quickly we'll do some numerical. Okay, so bulk modulus also we have studied. Okay, we have studied bulk modulus is B is equal to pressure divided
Minus
by
P by
del
del
V
V.
by V. Okay,
Minus.
so minus. That is the bulk modulus. So when you have a sphere, then you are applying
Decreasing.
you are applying some pressure from outside. So this is bulk modulus. Okay, so original volume V, then change in volume V minus delta V. So this is regarding bulk modulus. And we have studied shear modulus also. Okay. So there is a numerical on shear modulus we do first. Okay. So let it be a surface, and it was like this earlier. Now it got deformed. It got deformed like this. Okay. So let us say it gets deformed like this because of the force applied parallel to the surface. Okay. So I am applying a force parallel to surface, and on which area it is acting from the top. If you look, it will act on. If it is a rectangle, it will act on a rectangular area. You see from the top. Okay. The question is a square lead slab. So this is a lead slab. It is made of lead. It is a slab of 50 cm. Side 50 cm. So this is 50, this is 50, side 50 cm, and thickness 10 cm. Thickness is what you see. So if you see from the top, actually this you will see this as 10, right?
Yeah.
10 cm. This is top view. Okay. This is top view.
Yes, yes. Understood.
From the top, it will look like 10 cm. That is the thickness.
Yeah.
Thickness is perpendicular to the plane of the board. 10 cm is subjected to a shearing force of